Okay, hello everybody. My name is Zhenni Pan. Thank you for coming to the MARC lecture provided by the major in Computer Science and Communication Engineering. Thank you very much. Today I'm going to talk about a brief introduction on a very fundamental major course called Information Theory. Okay, so first of all, information theory, it was originally proposed by Claude Shannon. And does anyone hear about this name before? Okay, so Claude Shannon, in his published paper titled Mathematical Theory of Communication. So something sounds like complicated mathematical stuff, but due to Shannon's contribution, this theory has allowed us to build a digital world, to build some mechanism to browse in our current internet, to build digital communications, to build digital computers. Okay, so all the digital worlds are thanks to the contribution of Claude Shannon. There are two main problems are involved in these classes. So first one, how to represent information in a compact way. And the second one, how to access it without losing any information. Those are two core problems, okay, involved even for current systems. So information theory correspondingly tell us some solutions, how to build some methodology to solve those kind of problems. Then we mainly have two kind of topics, data compression and reliable communications. So I'm going to give some insights one by one. Okay, so firstly, let's consider a question. What is the weight of information? Can information be measured by some methodology? So suppose if you want to weigh the stone, what will you do? Maybe you say you need a balance machine, right? If you have a balance machine, it's easy for you to get the weight of the stone, right? And how about the liquid? Well, let's say maybe a bucket of water. Okay, use a bucket, then you can easily weigh the water, right? By using the balance machine. How about this? What is the weight of a book? Then you can also say, we can use balance machine, right? But, okay, maybe you got some value, 1.8 kilograms. But is it the correct weight to measure the information contents involved in this book? Maybe not that exactly, right? It seems the weight, just the physical weight of the book, right? So how to weigh the information? So let's try some ideas. Okay, so we know that the minimum component, or we say unit of a book, maybe we say it's a page, right? So if you can know the weight of a page, and you know the total weight of a book, then it's easy for you to know how many units compose a book. So how many pages in total, right? So if we know the units, so could we consider that, suppose we can define a basic unit for information, just something like a unit of information conveys in this paper. And if we can do this, we know the basic unit, then it's easy for us to quantify the total information for n units of this book, right? Okay, but still very intuitive. Now let's see another example. Example about weather forecast. So assume a city where it rains 1 day per year. So a year, 365 days. If we consider any day equally likely, just very fair days. So what would be the most informative weather information for you? Suppose we just say rainy or sunny. which one do you is most interesting for you, or you think is more necessary for you? Sunny or rainy? To this special city rains 1 day per year. Any idea? Or, so how many percent think sunny is important? Or anyone has idea about, okay, I think rainy is more important for me. Okay, thank you so much, so many people. Yeah, actually, I think so. Rainy is the correct answer, but why? So we know that we can suppose all the days are equally likely, right? So we can easily calculate the probability of at any day being sunny or rainy, right? So for example, sunny, then 364 over 365. And for probability for rainy will be just 1 over 365, because only one special day. So any day will be possible within a year. So why we say that rainy tell us more information? Because sunny, there's such high probability for just any day will be sunny during the year. If we don't have the weather report, it doesn't matter, right? We just assume probably tomorrow will be sunny. So it means sunny tell us less uncertainty of the weather, right? We are quite sure about this weather, okay? But for rainy, any day of a year could be rainy. So the uncertainty is really large. So it could be any day. So we have 365 choices, perhaps, right? So if we say the uncertainty of this information, rainy, so maybe the uncertainty is quite large compared to sunny, right? So somehow we can associate the relationship with uncertainty to represent the information, a kind of information contents. So Shannon actually defined a basic unit for a specific outcome. Then we name it as information contents, just like either for sunny or raining. Given a specific outcome, then we can always quantify the information contents for that outcome, which is related to the uncertainty of the event. So intuitively here, probability, right, is a kind of uncertainty. So, but uncertainty, the higher the probability, the lower the uncertainty. So uncertainty can be considered as the reverse of the probability, right? Okay, that is how we associate with uncertainty. And more than that, if we want to use some binary digits, binary numbers, 0 and 1, only 0 and 1, right? If we want to use binary numbers to represent those kind of uncertainty, how many bits, how many binary numbers should we use? Right? So if we use 1-bit binary numbers, we can represent 2 outcomes, right? 0 or 1, maybe two kind of uncertainties. So if we use 2 binary numbers, how many outcomes could be represented? 4? So maybe 0, 0, 0, 1, 1, 0, 1, 1. There will be 4 kind of situations, right? Can be represented by only 2, 0, 1 combinations, right? So suppose you have, we don't know the length. We just say length L. 2 to the power of L. This is the required length to represent by binary numbers describe this uncertainty. The uncertainty is, we say, just the reverse of the probability. How to calculate, how to obtain this L? By using logarithm operation, right? I'm not sure, maybe you have already learned in high school how to get this L. So we use log-based to operations to this uncertainty, which is the equation listed there, okay? So Until here, then you can find that maybe the minimum unit of if we say of information to a specific outcome can be quantified by this equation. Here, we use a small h to represent the minimum information length if we use binary numbers to represent this kind of information. So the units can be measured in bits. Okay, this because we talk about digital numbers. Okay, so based on this equation, then you can easily calculate any information contents, the information contents to any outcomes here, either sunny or either rainy. So especially for rainy case, you can find the information represent 8.5 bits. So maybe you are going to use 9 bits binary numbers, 01, 01, 01 combinations, totally 9 bits to represent this kind of uncertainty. How many uncertainty? For a year, 365 kinds of uncertainty. Okay, so we just use maybe 9 bits. 9 bits are enough to represent 365 kinds of uncertainty. So if you calculate 2 to the power of 8 or 9, it should be approximate to the number of 365. Okay. Okay, so information contents is the minimum unit to represent any information for a specific outcome here. Because the higher the uncertainty, so it conveys more information. The lower the uncertainty, it means there's not so many important information, right? Just like Zhenni. Okay, so if we know this, so how much information is conveyed by a daily weather report? So suppose the weather report can be considered as a kind of random variable, random things, right? Random event. The event has these kind of probability distributions. Either a day can be sunny or rainy in terms of these kind of probabilities, right? So how to calculate the average information for this event? So now we know the probability. We also know some fundamental information contents, minimum unit of the information. So based on probability theory, maybe you have already learned, we can always calculate the average value of a specific random variable by using expectation calculation, right? Expected value. So it's a kind of weighted average. So you can consider each information contents has some kind of weight. The weight is due to its probability, its occurrence, right? So we use the probability to weigh as a weight to weigh these information contents, and when we make a summation, then you can finally calculate or obtain a kind of average amount for this random variable, these random events, right? So here maybe you notice that we use a big capital H here. So the information, a kind of average information can be quantified for an random event called information entropy. So entropy is just a kind of expectation of the information contents. So information contents tell us any information for a specific outcome, any fixed things, either sunny or rainy, given you know the results. But entropy tell us average information for a random event, given some distribution. So we don't know tomorrow will be sunny or rainy, but we know how much probability for rainy for being rainy or being sunny, right? So we can assume some average information by using entropy. Okay, so those are two fundamental units to quantify information. Okay, now let's see some other examples. Okay, so now we have some hidden letters here. Could you read the sentence with those hidden letters? Anyone can read? Anyone want to try? Any idea? So let me try. So he's a handsome, clever, and rich man. Is it fine? Okay. Let's see another example. Anyone? Yeah. Thank you so much. We will have a midterm examination next week, but it's not true. Okay. So how about the last one? Any idea? A little bit difficult. Okay, it takes more time. And maybe you have more answers, more than one, right? Okay, it seems difficult. So I give one example. It is rainy today. Well, maybe you have other solutions, right? But why? Why you can read some sentence with some hidden letters while you cannot read sentence with some other hidden letters? Because our language, especially we say English letters have some redundancy. Not all the letters have a fair occurrence. Okay, so you can find a distribution of any English letters from A to Z. How about the occurrence if we say in a statistical value? So some letters are very often to be appear here, something like E and T, A, something. Those kind of letters are very easy to predict. So it means convey less information. Even those letters are hidden. We can still, we can predict what would be the information of the word, of the sentence, right? But some other letters, there are some letters which have low probability of occurrence appearing here. For example, Q, Z, something else. So those kind of low probability letters convey more information typically. So it means if without those kind of information, we are difficult to encode or say we can interpret the meaning of the sentence, right? Because those information are so important, convey more information. So that's why you can read some sentence with some stars, hidden letters sometimes, because those redundancy tell us less information. But some letters convey more information, but which are very important for us. Okay. So due to the information entropy theory, information entropy can quantify how many bits are required on average to represent information described by a random event. Okay, just like we squeeze the essence of event, we tell us the minimum essence of any event, what would be the information quantity, and how many bits are required if we want to represent it by using binary numbers. Okay, you may see some 0101s. Okay, and due to this theory, it's very useful for us to, we say, compress, reduce some size of very large files into some small size files. For example, your zip RAR files, right, in your computer. So maybe just use some shorter binary numbers as some codes, just represent your original very long, large files. So this topic is the first problem in this class, data compression. How could we compress a very large size of files into very small size of numbers, meanwhile guarantee low probability of errors? We don't want to lose any information, right? So if in a real transmission, so the sender will put your original source into some compressor, make some compression, got the essence of the information, and put those information into the channel. And for the receiver side, receiver can use a kind of equipment called the compressor to make a kind of interpretation, tell you the meaning, right? So after that, you will know the meaning of the original source. Okay, this is the first part. So now the remaining problem is how could we transmit those kind of compressed data through a channel? So I want to make some example of what is the channel here. Intuitively say, my voice can be heard by your ears, right? So the air will be the channel. And the information seen from your eyes can be transmitted or interpreted by your brain, right? So in this case, nerves will be the channel. And if the antenna on the Earth communicate information to some satellites, or we say we have some satellites on the Mars, the medium will be a vacuum. So channel is just a medium carried your information from sender side to receiver side, okay? Also, for example, if you store your information, your data into your hard disk, and next time you will read your data from the hard disk to process some other task. In this case, hard disk can also be a kind of medium, right? It can also be a channel, so channel is a wide meaning. Okay, so now I would like to make an example of a fundamental, very simple, basic communication system for voice communication, maybe. So we call that tin can telephone, a string phone. Have you played this toy before? Maybe not in your age, but in my age. Okay. So basically, the speaker just carry the phone, speak up, right? Talk something. So the voice will be vibrated while there's a rope, and transmit to the receiver side. Receiver, the people can carry another can, right, attached with the ear, then hear the voice. So because your brain can interpret the vibrations into signals. Okay, so it's a very fundamental system for voice or music transmission. So if the distance becomes longer, can they talk to each other as well? For example, Bob, Alice, the distance between them will be 10 kilometers. We are not sure. Who knows? But yeah, because voice, music, those kind of voice is a kind of mechanical vibration. It's a kind of analog, we say analog signal, a lot of irregular vibrations, right? And this kind of analog signal is very weak to conquer the noise. It's not good for long distance transmission. So Shannon tell us, okay, Shannon say, we can realize long-term transmission by using binary signals instead of analog signals. So binary, it means 0-1 digital signals, right? For a simple realization here, for example, Alice plunk the rope. Then the Bob can hear some clear vibration. Because 0-1, maybe it's very easy. Only two symbols can be represented by maybe high voltage, low voltage. You can assume a very heavy plunk, right? Or a very weak plunk. Only two kind of signals, very easy to be identified by the receiver. So, okay, so Alice now plunked the rope, then Bob can hear some voice, okay? It's just like with or without some vibrations, right? So by this mechanism, they can talk with each other even over a long distance. But our real transmission, our real world, includes a lot of noise. So noise means we cannot guarantee that Alice send a 0, then Bob can also receive a correct information as 0, right? For example, if, Alice just slightly plunked the rope, suddenly the sky, there's a very heavy rain. Rain drops on the rope. Then for Bob's side, maybe he just heard a very heavy plunk. Okay, so Bob think, okay, Alex sent me a 1, right? Just a very natural noise from our world. So we must have some treatment in this case, because due to the noise, there will be even a very small probability that the bit will be flipped to something else. So 0 may be flipped to 1, 1 may be flipped to 0, okay? So very easy treatment here. For example, when Alex sent 0, she sent not 1 0, not a 0, but we sent 0 3 times. Alex sent the 0 repeatedly, okay? So Bob will receive, okay, 0 1 0. It means the second bit gonna be flipped here, right? But we know that the error will be continuously happen for 3 times. It's almost impossible, right? The probability of that weird case is really low. So for simple solution to Bob just trusts the majority vote, most of the similar case. So Bob just count how many similar bits gonna be received. So now Bob trusts that, okay, Alice sent me 0, it's not 1. Okay, it's a very easy treatment, but help us to detect and correct the error. Okay, that's another problem of this course, which means like, if we draw a big picture of a communication system, so firstly, we talk about data compression, how to represent a huge source by using some shorter binary numbers. So after that, we talk about how to guarantee a reliable communication via some noisy channel. So if in this case, we need some channel coding theorem by using equipment of encoder or decoder for each side. Okay, so based on those two problems here, we can find a huge big picture of a fundamental configuration of a communication system here. Okay. Okay, so if we summarize the contribution of the information theory, so before Shannon, people always use analog signals, which is very weak to conquer the noise, very easy to have errors. So after Shannon, people changed to the digital world, right? And Shannon also tell us theoretically how much data can be transmitted without any loss of the information. This is also another achievement. So before Shannon, we think that if we want to have no error, free of error transmission, it's almost impossible. If we say rate represent the communication speed, how many speed can be achieved. So the rate also approximates to 0. So it's almost impossible, right? If once you transmit, then you must create some error. After Shannon tell us some theoretical boundary until what kind of rate transmission ability that we can achieve free of error transmission with very low, almost 0 transmission errors. That's also the contribution of Shannon. Okay, so this is two basic questions for these classes, information theory. So data compression and how to achieve reliable communication via the noisy channel. And this course, information theory, is really powerful and widely used in a lot of areas. Not only computer science, communication theory, but also physics, mathematics, probability, statistics, and economics. A lot of areas can use this kind of, can use the theory from Shannon if we talk about digital world, okay? So this is a brief mini introduction on this topic. Hope you are interested in this class. Thank you for your listening. So those kind of things maybe you will learn in any other future university courses. Okay, thank you very much.